So welcome back, Level 3 physicists. Continuing on with AC currents for the Level 3 external on electromagnetism and electricity. Today looking at inductors in AC. So in terms of inductive circuits, when an inductor is in an AC circuit, the current's constantly changing. That means they're going to get a constant change in magnetic flux within the inductor. So, as we've seen with inductors earlier, this creates a back EMF that opposes the change in current. Therefore, current and voltage are not in phase. This time, which is the opposite of a capacitor, the current is 90 degrees behind the voltage this time. Okay, so just like we had reactance for a capacitor, you can also have it for an inductor. So the energy supplied this time in an inductor is stored in the magnetic field and returned when the field collapses. But in AC, it doesn't collapse. Therefore, no energy is dissipated. So basically, the reactance is the effective resistance of the inductor in AC. So the equation is that the reactance of an inductor equals omega L, okay, where omega is 2 pi F. And you can just use it like Ohm's law as well, where the supply voltage will equal the current times XL. And XL being effectively a resistance has the units of ohms, and angular velocity and inductance we've already looked at before. So in terms of an RL circuit in AC, very similar to the RC circuit, you'll also get impedance, just like you would with a capacitor. Okay, and it's also measured in ohms. Okay, so again, you can apply Ohm's law, so the supply voltage will be equal to the current times the impedance. So this impedance for a resistor, both the current and voltage is in phase, as we already know from our previous lesson. For the inductor, the current now lags the voltage by 90 degrees. Therefore, the resistance voltage lags the voltage across the inductor by 90 degrees, as you can see by the vector diagram. So therefore, just like for the capacitor, the impedance can be calculated with Pythagoras. This time Z equals the reactance of the inductor squared plus the resistance squared, take the square root of that, and the analogous for the supply voltage, where the voltage across the inductor all squared plus the voltage across the resistor all squared, take the square root of that from the sum, and you get the supply voltage. And the phase angle for the impedance supply voltage now for a inductor is going to be sine theta, due to the change in direction of the phase, which is equal to the reactance of the inductor divided by the resistance, or the voltage of the across the inductor divided by the resulting voltage across the resistance. Okay, so just to summarize that, I use the mnemonic Eli, the Iceman. So E stands for EMF, voltage. Okay, so the voltage always leads the current in an inductor, and the current always leads the voltage in a capacitor. So maybe you'll also find that useful.